In this video, we're going to be doing problems from 11.2 having to do with sequences. For this first example, we want to determine whether the sequence as the limit as n approaches infinity for negative 2n plus 5 divided by 2 raised to the n power is divergent or convergent. And we're asked that if it is convergent, to evaluate its limit. So we want to take a look at the definition that we have on here. So definition 1 says, if the terms of a sequence a sub n approach a number L as n increases, then the limit as n approaches infinity of a sub n is equal to L. So what we're basically told is that if the sequence has a limit, so if the sequence exists and it has a limit, then it converges. But if the sequence does not have a limit, or as they say otherwise, then we have that the sequence diverges. Okay, with this in mind, so let's take a look at the problem. We have the limit as n approaches infinity of negative 2n plus 5 over 2 raised to the n power. So as we kind of evaluate the limit for this, we can kind of notice that if I was to plug in infinity here, it would be negative 2 times infinity. And that would pretty much tend to negative infinity. And if I was to plug in also infinity for this n here, then it would be 2 raised to infinity, which is a very large number, and 5 divided by a very large number just tends to be 0. So here we would have negative infinity plus 0, which would give us that this is a very large negative number. And because this is a very large negative number, we say that it doesn't exist, but also because it tends to negative infinity, we say the sequence diverges. So example number 2 says, determine whether the sequence as the limit as n approaches infinity 5 plus 0.25 raised to the n power is divergent or convergent. If it is convergent, then evaluate its limit. So this is very similar to the first problem. So we're going to write down our problem. The limit as n approaches infinity of 5 plus 0.25 raised to the n power. So if we're able to evaluate its limit, then we can pretty much determine whether it's divergent or convergent on here. So as we evaluate the limit, we take a look at what would happen if we plug in infinity for our value of n. Then it happens that we only have that value of n here. So if I was to plug in our value of n there, then that would mean that this is 0.25 raised to a very large number. And because it's raised to a very large number, this would actually tend to 0. And then we would have 5 plus 0 as we evaluate the limit, because as we evaluate the limit of just the constant, then we get its constant in return, right? So there's nothing to evaluate because it doesn't involve any variable n. And so 5 plus 0 is just 5. And because we have a value, we have a constant as our answer, we can say that the sequence converges specifically to the value of 5. And that is all for this problem. For example 3, we're asked to find the limit of a sequence such that a sub n equals to cosine of n divided by 2 raised to the n power. In this case, we're going to use theorem 3. And theorem 3 says if the limit as x approaches infinity of f of x equals to L and f of n equals to a sub n, when n is an integer, then the limit as n approaches infinity of a sub n equals to L and a sub n converges to L. So basically, this theorem tells us we determine the limit of a sequence the same way we determine the limit at infinity of a function. So let's write our given sequence as a limit as n approaches infinity, and we have sequence cosine of n divided by 2 raised to the n power. All right, so let's start talking about what happens when we plug in infinity for these variables of n here. So let's take a look at the denominator first. So the denominator first says cosine of n. If we were to plug in infinity on there, we got to recognize that the range for cosine is between -1 and 1. It's actually not gonna ever touch any of those values on there. So we can kind of just look at that for right now and then start talking about now the denominator and then make our assumption of what's going to happen after we look at our denominator. So if we look at our denominator, as we plug in a value, a very, very large value there for our n as our exponent, we would get that it's just going to tend to infinity. So this would happen to be a value between -1 and 1 for cosine in the numerator divided by a very, very large number in the denominator. Regardless of what value you pick for the numerator, this is going to get divided by a very large number. So this is going to equal to 0. So if it's equal to 0, then we get that a sub n converges to 0. So example number 4 looks very similar to example number 3, and it's asking us to find the limit of a sequence, and we're given this sequence. And so remember that we're using theorem 3 because theorem 3 tells us we determine the limit of a sequence the same way we determine the limit at infinity of a function. So let's write this as the limit as n approaches infinity of 7n squared plus 1n plus 3 divided by 6n squared plus 5n plus 4. So we have general guidelines to finding limits at infinity of rational functions. And so remember that one of them is to divide each term in the numerator and the denominator by the highest power of x in the denominator. So in this case, we have that the highest power here in the denominator is n squared. So what we're going to do is we're going to write the limit as n approaches infinity. We're going to take all the values that we have on here. So 7n squared plus 1n plus 3 divided by, so here we want to write them as we're going to divide everything by n squared. And so in the denominator, we have 6n squared plus 5n plus 4. We're dividing everything once again by n squared. Okay, so when we simplify this a little bit, notice that on here, I'll do it in another color, these n squares cancel out. And what ends up happening between these two is that we're just left with n to the first power, and the first one, well, the numerator one gets canceled. Here, there's nothing to really simplify, so this stays the same. Here, the n squares cancel out, and we're just left with 6. Here, something similar happens to what we had for 1n at the top, and we're just left with 5 divided by n to the first power. And here it's already simplified. There's nothing else to do. So we can rewrite this as the limit as n approaches infinity of 7 plus 1 over n plus 3 over n squared all over 6 plus 5 divided by n plus 4 over n squared. And now we can evaluate our limit. So what I'm going to do here is write it in another color and say, so as we evaluate the limit as n approaches infinity, for 7, nothing happens, and nothing happens for 6 as well, since they're just constants. But as we look at 1 over n, so 1 divided by a very large number, that tends to 0. And it's something similar for this on here as well. 3 divided by infinity to the second power is just a very large number. So 3 divided by infinity is just tending to 0. And something similar happens to 5 divided by n. 5 divided by infinity tends to 0. And 4 divided by infinity squared just tends to also 0. So what we're left with is just 7 and 6. So this is our answer. We say that a sub n converges to 7 over 6. Before we move on to another example, I want to show you a shortcut to solving example number 4. So we take a look at this, and it says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. But also, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficient. Also, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So for example 4, if we take shortcut number 2, which tells us the degree of the numerator is equal to the degree of the denominator, then we take the leading coefficient. So in this case, we look at 7n squared and 6n squared. And so because they have the same degree for both the numerator and the denominator, then we just take the leading coefficients, so we have 7 over 6. So if you remember some of these shortcuts, it makes evaluating these limits a lot faster. Example number 5 is asking us to write down the first 3 terms of the sequence. And so we have a sub n equals to n plus 2 factorial all over 2n squared minus n plus 6. So let's start off with first a sub 1. And if we write a sub 1, so we're going to pretty much substitute in our value here for wherever we see an n. So we're going to have 1 plus 2 factorial all over 2 times 1 squared minus 1 plus 6. And so we're going to simplify this a little bit, and we're going to get 3 factorial all over 2 minus 1 plus 6. And so we got to remember that for a factorial, it's pretty much capturing all the values before the value that we see on here. So in this case, before 3, there's 2 and there's 1, and it's taking the product of all those numbers. So that's pretty much what the factorial here is saying. So we're going to get 3 times 2 times 1. And so in the denominator, when we simplify this a little bit more, we get just the value of 7. Now, normally at this point, we would either break down 7 and try to see if any value is going to cancel out with the ones in the numerator here. But in this case, only 1 goes into 7. So there's no point of doing much more. So this is 6 over 7. Now let's try out the second value in the sequence. So on here, we're going to replace now n with 2. So we'll have 2 plus 2 factorial all over 2 times 2 raised to the second power minus 2 plus 6. This is equal to, so we simplify the top, 2 plus 2 is just 4 factorial. And then on the denominator, we get 2 squared times 2 gives us 8 minus 2 plus 6. Once again, we're going to pretty much expand the factorial here and say 4 times 3 times 2 times 1 all over. And once we simplify the denominator a little bit, we get 12. And now at this point, we do see that there are some values that are going to go into 12. We can actually capture that 4 and 3 pretty much gives us 12. So all that we have left is just 2. Let's do one more. A sub 3. So in this case, we're going to replace every value of, well, every n with a value of 3. We'll have 3 plus 2 factorial all over 2 times 3 raised to the second power minus 3 plus 6. And so we simplify the top and we get 5 factorial all over. So 3 to the second power times 2 gives us 18 minus 3 plus 6. So let's expand out the factorial. And we're left with 5 times 4 times 3 times 2 times 1. And so in the denominator, we simplify this a little bit and we're left with 21. Now on here, 21, the only value that goes with it is this 3. So 3 goes into 21 7 times. We pretty much get the product of the values that are left over at the top. So 5 times 4 times 2 times 1 gives us 40. And the denominator, we're just left with the 7. And those are the first 3 terms of the sequence. For our last problem, example 6 says for the recursive formula defined by a sub 1 equals to 1, a sub 2 equals to 1, and a sub n equals to a sub n minus 1 plus a sub n minus 2, and we're asked to find the first 5 terms. So let's start off with the terms that they give us. So they're telling us a sub 1 equals to 1. That's the first term. And we get that a sub 2 equals to 1 as well. So those are the first 2 terms. Now, if we want to find any more terms in the sequence, then we have to refer to this format here. So let's say a sub 3. So if we get a sub 3, then we would have a sub, well, here we would plug in our n value. So 3 minus 1 plus a sub. Once again, we're plugging in our n value. So 3 minus 2. And so this gives us a sub 2 plus a sub 1. And since we have these 2 values, a sub 2 is just 1 and a sub 1 is just 1, then we get 1 plus 1 equals to 2. Now for a sub 4, we have a sub 4 minus 1 plus a sub 4 minus 2. And so we simplify this a little bit, and we have a sub 3 plus a sub 2. And so a sub 3, we have this value, it's 2. And then a sub 2 is just 1. And so we simplify this, and 2 plus 1 is just 3. Let's do one more. So a sub 5. So we have a sub 5 minus 1 plus a sub 5 minus 2. And so simplifying this a bit, we get a sub 4 plus a sub 3 equals 2. So a sub 4 is 3, as we just found out. And then a sub 3 is 2. So 3 plus 2 is just 5. And those are the first 5 terms in the sequence.